Once again, I welcome in the class of hydraulic engineering. So in the last class, I have discussed about the what is rapidly varied flow and the example of rapidly varied flow. And after that, I have discussed the what is hydraulic jump, and then what is the various application of hydraulic jump. And then I have discussed the hydraulic jump in a horizontal rectangular channel. And in horizontal rectangular channel, we have derived the relationship between the conjugate depth, and then relationship between the conjugate depth and Froude number. So today I will discuss the what is the relationship between the Froude number at the beginning of the jump and Froude number at the end of the jump, and then what is the energy loss, and after that what is relative energy loss, and then efficiency of the jump, and what is the expression of length of the jump and height of the jump. And then I will discuss the various types of jump, and in the various types of jump I will classify these various types of jumps on the basis of initial Froude number. So let us discuss about the relationship between the Froude number at the beginning of the jump and at the end of the jump. So let us assume f1 be the Froude number at the beginning of the jump, and f2 be the Froude number at the end of the jump. So Froude number for a horizontal rectangular channel can be written as f1 is equal to v by square root of g by 1, or we can write q by b into y1 into square root of g by 1, and q by b can be written as q by square root of g into y1 q. So f1 square can be written as q square divided by g y1 q. Similarly, f2 square can be written as q square by g into y2 q. So if I write f1 square is equal to q square by g into y1 q, or if I write q square by g into y1 q into, here we can write into y2q divided by ytq. So q square by g y2q can be written as f2 square. So we can write f1 square is equal to f2 square divided by y1 by y2 whole cube. And we have the relation y1 by y2 is equal to 1 by 2 minus 1 plus square root of 1 plus 8 f2 square. So if I put the value of y1 by y2, so we can write f1 square is equal to f2 square divided by y1 by y2 can be written as 1 by 2 into minus 1 plus square root of 1 plus 8 f2 square whole cube. So it can be written as f1 square is equal to 8 f2 square divided by minus 1 plus square root of 1 plus 8 f2 square whole cube. So this is the relationship between the Froude number at the beginning and end of the jump. Now I am going to derive the expression of energy loss. So let EL be the energy loss. So this energy loss can be written as EL is equal to E1 minus E2, and E1 can be written as Y1 plus V1 square by 2G minus Y2 plus V2 square by 2G, or if I write Y1 plus Q square by 2G A1 square minus Y2 plus Q square by 2G into A2 square. So here we can write Y1 plus A1 can be written as B into Y1 square. So Q square by B square can be written as Q square by 2G into Y1 square minus Y2 plus Q square by 2G into Y2 square. So Y1 minus Y2, EL can be written as Y1 minus Y2 minus it can be written as Q square by, it can be written as plus, here plus Q square by 2G into Y1 square minus Q square by 2G into Y2 square. So EL can be written as Y1 minus Y2 plus Q square by 2G 1 by Y1 square minus 1 by Y2 square. So EL can be written as Y1 minus Y2 plus Q square by 2G Y1 square into Y2 square, and it can be written as Y2 square minus Y1 square. So EL can be written as Y1 minus Y2 plus Q square by 2G Y2 square minus Y1 square can be written as Y1 plus Y2 into Y2 minus Y1 divided by Y1 square into Y2 square. So if I take the common Y2 minus Y1, Y2 minus Y1, so it will be minus 1 plus Q square by 2G Y1 plus Y2 divided by Y1 square into Y2 square. And we have the relation Y1 Y2 into Y1 plus Y2 is equal to Q square by G. So EL can be written as Y2 minus Y1 into minus 1 plus Y1 Y2 into Y1 plus Y2 by 2 into 2, it will be Y1 plus Y2 plus Y2 divided by Y1 square into Y2 square, Y1 square into Y2 square. So EL can be written as Y2 minus Y1 into Y1 Y2 cancel, so it will be minus 1 plus Y1 plus Y2 whole square divided by 4Y1 Y2. So energy loss can be written as Y2 minus Y1 into 4Y1 Y2 and Y1 square, so it can be written as Y2 minus Y1 whole square divided by 4Y1 Y2. So energy loss will be Y2 minus Y1 whole cube divided by 4Y1 Y2. So this is the energy loss in a horizontal rectangular channel. This is the expression of energy loss in a horizontal rectangular channel, where Y1 is the pre-jump depth and Y2 be the post-jump depth. Now relative energy loss. So relative energy loss is the energy loss divided by initial energy or energy at the just beginning of the jump. Similarly, the efficiency of jump can be computed the ratio of energy at the end of the jump to the energy at the beginning of the jump, or E2 can be written as E1 minus EL divided by E1. So it will be 1 minus EL by E1, and this EL by E1 is the relative energy loss. So the efficiency of jump can be written as 1 minus relative energy loss. Height of the jump. So height of the jump is the difference between the vertical distance between the end of the jump and toe of the jump. So it will be y2 minus y1. Similarly, relative height of the jump is the height of the jump divided by energy at the beginning of the jump. So it will be hj by e1, and hj can be written as y2 minus y1 divided by e1. Similarly, the relative initial depth. So relative initial depth is the y1 divided by e1. Relative sequent depth means at the end of the jump the depth is y2 divided by e1. Length of the jump is defined is the horizontal distance between the toe of the jump to a section where the water surface level off after reaching the maximum length. And the length of the jump is generally 5 to 7 times the height of the jump. And the height of the jump is y2 minus y1. So it can be 5 into y2 minus y1 to 7 into y2 minus y1. Experimentally, it has been also found that length of jump is equal to 6.9 into y2 minus y1. And when Froude number is less than 5, so the Lj by y2 is the function of initial Froude number. And similarly, when the Froude number is greater than 5, so Lj by y2 is equal to 6.1. There are various types of jump like undular jump, weak jump, oscillating jump, and steady jump, and strong or choppy jump. So on the basis of initial Froude number, we will classify these 5 types of jump. Like for the undular jump, our Froude number is lies between 1 to 1.7. Similarly, in case of weak jump, our Froude number is lies between 1.7 to 2.5. And for the oscillating jump, the initial Froude number lies between 2.5 to 4.5. And for the steady jump, our initial Froude number lies between 4.5 to 9. And for the strong or choppy jump, our initial Froude number is greater than 9. So with the help of initial Froude number, we can classify the various types of jump. So depending on the value of Froude number of incoming flow, there are 5 distinct types of hydraulic jump. It should be noted that the Froude number of incoming flow, that is F1, should be always greater than 1 for supercritical flow for hydraulic jump to occur. So this is the first jump, that is undular jump. As I told you that our initial Froude number lies between 1 to 1.7, including 1.7, and the relative energy loss is approximately equal to 0. Means EL by E1 is approximately equal to 0, and water surface is undulating with a very small ripples on the surface. Here we can see that this type of jump is generally not observed. So this type, the sequent depth ratio is approximately equal to the 0, and small ripples will form in case of undular jump. And the important thing that is we have to remember this point. Our initial Froude number lies between 1 to 1.7. Similarly, in case of weak jump, our initial Froude number lies between 1.7 to 2.5, and relative energy loss is approximately equal to 5 to 18%. A series of small rollers forms. We can see that this is the small roller forms on the jump surface, but the downstream water surface remains smooth. Similarly, the third jump is that is called oscillating jump. So the entering jet of water oscillates in a random manner between bed and surface. And in case of oscillating jump, our initial Froude number lies between 2.5 to 4.5, and the relative energy loss is lies between 18 to 45%. Similarly, in case of a steady jump, our initial Froude number lies between 4.5 to 9, and relative energy loss lies between 45 to 70%. The jump is well established, and the roller and jump is fully developed to cause applicable energy loss. So this type of jump is generally developed, and this jump is well established, and the roller and jump is fully developed to cause the applicable of energy loss. And the important thing that the initial Froude number lies between 4.5 to 9. Similarly, the last jump, that is also called strong jump or choppy jump. This is the most efficient jump in which energy loss is maximum, and initial Froude number is greater than 9, and relative energy loss is greater than equal to 70%. During this jump, water surface is very rough and choppy, which continues downstream for a long distance, and sequent depth ratio is quite large. So here we can see that this is the example of the strong or choppy jump. And in case of non-prismatic or in case of non-rectangular channel, uh, jump in horizontal non-rectangular channel, so in that the basic equation is specific force will be constant, means q square by ag plus a z bar is equal to constant. So in case of non-rectangular channel, uh, we cannot use the whatever we have derived the relation between the conjugate depth, relationship between the conjugate depth and the Froude number, and the relationship between the Froude number at the beginning of the jump and at the end of the jump, and similarly the various expression we cannot apply directly, because that formula is applicable for horizontal rectangular channel, like the relationship between the conjugate depth, like y1 y2 into y1 plus y2 by 2 is equal to q square by g. So this formula is applicable for only rectangular channel. In case of non-rectangular channel, we have to derive the relation, or directly basic equation we can apply q square by ag plus az bar is equal to constant, and we will get the relationship accordingly. Similarly, the relationship between the conjugate depth and the Froude number, like y1 by y2 is equal to 1 by 2 minus 1 plus square root of 1 plus 8f2 square, or y2 by y1 is equal to 1 by 2 minus 1 plus square root of 1 plus 8f1 square. So that is applicable for only horizontal rectangular channel. Similarly, today I have derived the relationship between the initial Froude number, so that is also applicable for the rectangular channel. And similarly, the energy loss, whatever we have seen, that is EL is equal to y2 minus y1 whole q divided by 4 y1 y2. So that is applicable for the rectangular channel. But in case of non-rectangular channel, EL is equal to, we can write E1 minus E2, and E1 can be written as y1 plus v1 square by 2g, or similarly E2 is y2 plus v2 square by 2g. Accordingly, we can derive in case of non-rectangular channel also. So let us take a few problems based on this. So the first problem is, the conjugate depth for a hydraulic jump in a rectangular channel are 0.5 and 2 meter. So we can see, if I make the this is end of the jump and beginning of the jump. So this depth is given, that is 0.5 meter, and this depth is 2 meter. So energy loss can be computed. Energy loss is equal to y2 minus y1 whole cube divided by 4 y1 by 2. So we can find 2 minus 0.5. So it will be 1.5 whole cube divided by 4 into y1. So it will be 0.5 into 2. So this value will be 1.5 whole cube divided by 1.5 to the power 3 divided by 4 into 1. So it will be 0.84. So D option is correct. The value is 0.84 meter. Let us take the another problem. At a hydraulic jump, the depth at two sides are 0.4 and 1 meter. The head loss in the jump is, once again the same problem. Let us assume this is the hydraulic jump. This is the beginning of the jump and end of the jump. So this depth is given, that is 0.4 meter, and this depth is 1.4 meter. So energy loss can be written as, energy loss is equal to y2 minus y1 whole cube divided by 4 y1 y2. So y2 is 1.4 meter. So 1.4 minus 0.4 whole cube divided by 4 into 0.4 into 1.4. So it will be energy loss 1 divided by 4 into 0.4 into 1.4. So it will be 0.45 meter. So D option is correct. For Froude number of a hydraulic jump, as 5.5. So the jump can be classified as. So we have seen that for various initial Froude number, in case of undular jump, we have seen that Froude number is lies between 1 to 1.7. In case of weak jump, we have seen that Froude number is lies between 1.7 to 2.5. Similarly, in case of oscillating jump, we have seen that the Froude number is lies between 4.5. In case of steady jump, Froude number lies between 4.5 to 9. And in case of strong or choppy jump, initial Froude number is greater than 9. So here the Froude number is 5.5. So it will be steady jump. D option is correct. At a hydraulic jump, the depth at two sides are 0.3, that is the pre-jump depth, and 1.2 meter, that is the post-jump depth. So let us assume y1 be the pre-jump depth, so that is 0.3 meter, and y2 is 1.2 meter. So the head loss in the jump and type of jump respectively. So head loss is equal to y2 minus y1 whole cube divided by 4 into y1 y2. So energy loss can be computed as y2 minus y1 whole cube divided by 4 y1 y2. So y2 minus y1 is 1.2 minus 0.3. So it will be 0.9 whole cube divided by 4 into 0.3 into 1.2. So it will be 0.9 whole cube 0.9 to the power 3 divided by 4 into 0.3 into 1.2. So it is coming 0.5 meter. So energy loss is 0.5 meter. Similarly, we have to identify the type of jump. So on the basis of initial Froude number, we have to identify the types of jump. So here y2 by y1 can be written as y2 by y1. So 1.2 divided by 0.3. 1.2 is divided by 0.3. So it will be 4. And we have the relation y2 by y1 is equal to 1 by 2 into minus 1 plus a square root of 1 plus 8 f1 square. So y2 by y1 is 4. So 4 into 2, it will be 8 is equal to minus 1 plus a square root of 1 plus 8 f1 square. So 8 plus 1, 9. 9 square, it is 81 is equal to a square root of, 81 is equal to 1 plus 8 f1 square. 1 plus 8 f1 square. So f1 is equal to 81 minus 1, 80 divided by 8, 10. So square root of 10. So it will be f1 is equal to the square root of 10 means it is 3.16. 3.16. So Froude number, initial Froude number lies between 2.7 to 4.5. So when the initial Froude number is lies between 2.7 to 4.5, so it is oscillating jump. So it will be oscillating jump. So C option is correct, because Froude number is lies between when initial Froude number lies between 2.7 to 4.5, so it will be oscillating jump. So oscillating jump. Let us take the another problem. So this question is asked in Engineering Services Examination 2014, 8 marks. A hydraulic jump takes place in a horizontal frictionless triangular channel. So remember in mind that this is the triangular channel, or we can see that it is a non-rectangular channel. So the basic equation is specific force will be constant with the bottom angle of 90 degree. So let us assume this is our triangular channel and the bottom angle is 90 degree, and this is, let us assume y. This angle is 19, so this is 45, so this is also 45, so this value is y, this is also y. So top width we can write 2y. So basic equation is that is, and pre-jump then and post-jump is given. Y1 is 0.5 centimeter, means 5 by 0.05 meter, and y2 is 0.15 meter. So we can write basic equation that is specific force at 1 is equal to specific force at 2. So the specific force at 1 we can write, it will be q square by a1 into g plus a1 z1 bar is equal to q square by a2 into g plus a2 into z2 bar. So we can write q square by a1 can be written as 1 by 2 into 2y1 into y1 into g plus a1 z1 bar. So it will be y1 square, because the area is 1 by 2 into 2y1 into y1, so 2 cancel, so it will be y1 square, and z1 bar is y1 by 3 is equal to q square by a2. So a2 is y2 square g plus y2 square into y2 by 3. So we can write q square by y1 square into g plus y1 q by 3 is equal to q square by y2 square g plus y2 q by 3. So if I put the value of pre-jump depth and post-jump depth, then we can compute the value of discharge. So q square by g into 1 divided by 0.05 whole square divided by 0.15 whole square is equal to 1 by 3, 0.15 whole cube minus 0.05 whole cube. So if I put the value of pre-jump depth and post-jump depth, so we can compute q square by g, and this value is q square by g into 355.56 is equal to, this value is coming 1 by 3 into 0.15 whole cube minus 0.05 cube, it is 1.083 into 10 to the power minus 3. So q square can be written as q square is equal to 1.083 into 9.81 into 10 to the power minus 3 divided by 355.56. So q can be computed as square root of this value. So square root of 1.083 into 9.81 into 10 to the power minus 3 divided by 355.56. So it is coming 5.47. It is coming 5.47 into 10 to the power minus 3 meter cube per second, or we can write q is equal to 5.47 liter per second. So the discharge in the triangular channel is 5.47 liter per second.